Okay, now let's calculate the input resistance of a push-pull configuration. Okay, so the same thing, we are what we are doing actually is to our case study is still class AB amplifier. Okay, so looking into the circuit, this is our circuit. Okay, now we should know about, you know the characteristic of the circuit. Like when we look into the circuit composition, we should know that what sort of amplifier it is. So it is it is a push-pull amplifier. Why? Because we have Q2, Q1 and Q2. This is a class AB amplifier. Why? Because we have an extra biasing at the base for this one, and then we have extra biasing for this at the base for Q2. So basically now this is our class AB push pull. Okay, and this is a single supply. Now why? Because we have only operating from single source, which is VCC, the rest is ground. So this is the description of the circuit. By this I mean that we should be able to comprehend a circuit by looking into its structure or composition. Now the input resistance, if you see the input resistance of this circuit is shown over here. Okay, this is, it has on how many, it has two emitter followers. Okay, common collector configuration. So basically if you see the emitter follower is right, the Q1 and Q2, they are the common collector configuration, so they call it as a emitter follower. So this one is emitter follower, common collector configuration. Okay, but if you see the main thing that during the operation only one transistor is active. Okay, for the input, for the input signal. So either this one is active, okay, or this one is active. So it means the effective transistor would be 1. Okay, so it means that if the effective transistor is equal to 1, so you have to take the resistance, equivalent resistance of a single transistor, not of two transistor. So by input impedance, remember, by input resistance, this parameter, okay, this input resistance is an equivalent resistance of biasing resistance. Okay, which will be of biasing resistance. So R1 of biasing resistance, R1 parallel to how many biasing resistors you have, R2. And since I told you that though it has two complementary Q1 and Q2 transistor, but one of the transistors is active, so it means that I am going to take the resistors only one, okay, the internal resistance of Q1 or Q2. Now remember, the input resistance of this is defined by okay, this value. Okay, for a common collector we did last time, that this Q1, so basically this is RQ1, RQ1, this is R, right? So this is RQ1 is basically equal to beta AC RE in prime, and these are the biasing. So remember that you have to keep things okay in your memory, that input resistance, okay, is the total equivalent resistance of which combination of the biasing as well as the input resistance of Q1. Anyhow, so this is done. Okay, over RE, there, can you see RE? There is no RE, but the emitter is connected to RL over here, right? Okay, so that's why we can replace RE with RL. So it means the input resistance, okay, the equivalent input resistance of class AB push-pull amplifier is given by this, and it is, we can prove that it has a small value. Let's check it with an example. If we see that if each bias, this is an example over here, okay, if each bias resistor is 1 kilo, so R1 is 1 kilo, R2 is 1 kilo, okay, and then if the complement transistors is a push-pull amplifier, AC beta is 50, so beta is 50. Okay, the load resistance is 8 ohms. Okay, the load resistance is 8 ohms, and RE prime is equal to 1 ohms. Okay, so what is the input resistance? So you put the value in this equation. Okay, put input 50 for beta, RE is 1, load is 8, and this is the parallel combination of 1 and 1, R1 and R2. It comes out to be 236 ohms. Now, so the input is just too small. Okay, so now remember, if you have an input resistance too small, so it would affect the gain. From previous studies and previous knowledge, we have this concept that it would affect the gain. So if you have a smaller value of input resistance, so the gain would reduce. Okay, so for that, what we do, we go to increase the input resistance. Okay, to increase it, this input resistance, we use, okay, another version. We modify a bit the circuit to Darlington class, Darlington case, and this is shown over here. Now if you see over here maybe, okay, so in Darlington pair, okay, what we do, we are, instead of a single Q1, okay, we have a pair of these transistors. Okay, a pair of transistors, to two pair of, okay, two Darlington pairs. Okay, two Darlington pairs, four transistors you can see. And since you have four transistors, so to mitigate or to overcome the cross over distortion, so we need four diodes. Okay, four diodes. In this case, we can see we have a combination of four diodes. Now this would increase the input, the R in. Basically it would, you will get a good input R in for that, right? Okay, this would increase. Okay, because this is increased because of some factors. Why? Beta is increased, it is square. Now we know that this is for a single transistor, but when a Darlington pair, this beta become beta square. Okay, so this is like 2. Okay, with the value, this is square, so this become 2, or RE is 1, RL is 8, R1 is okay. And the next thing is R1 and R2 for this Darlington pair. Okay, normally we take these values R1 and this R2 as higher values as compared to a single push-pull case. Okay, if it is not Darlington, so it means that this is further increased. So it means beta is increased. Okay, this part beta is increased, the base resistances are increased, because for Darlington we need lesser, so you should increase the resistor values to get a lesser current. So the input resistance as a whole, or the input resistance, would increase. Okay, now this increases. Okay, this increases. Okay, and this beta increases by you can see over here by a square. Okay, so it means Rn gets increase.